When we think of pressure, we always associate it by the force that's being applied. So if someone shoves us or someone taps on us, we feel the pressure. Or when we swim underwater, we feel the pressure of water, and even more so as we go deeper and deeper down the pool. But we never think about pressure when it comes to the atmosphere or the air that's surrounding us. That's because it's our norm. We already are used to the fact that air or how we move, nothing is restricting us, right? But ask that to an astronaut who's been in space for 6 months and then comes back here on Earth, and he'll say that he can feel the difference. Okay, so the first one who discovered that atmosphere is actually putting a pressure on us is this Italian guy called Evangelista Torricelli. He did this experiment, which is very, very crude. He created a capillary tube. He fused the bottom end, and then he opened the top portion of this tube, and he filled it completely with mercury all the way to the brim. He then have a little dish that also contains mercury, and then he inverted this tube and then quickly inverted this tube into the dish. He said that if there's no pressure in the atmosphere, then all of this liquid will just drain down and flows down into the dish. But what you notice is that there's a certain level at which this mercury will drain, okay, and then it will completely stop. He noticed that every time he did this experiment, the level of mercury is always at 760 millimeters in length from this distance, okay, all the way to the top. It's 760 millimeters in length. So he said that the pressure of the atmosphere must be equivalent to this height. So the pressure of the air here, it's pushing this liquid, and it's keeping all of this liquid inside the capillary tube from draining out. So it's kind of like a revolving door, not really a revolving door, but a door between in the restaurant where it kind of swings in both directions. So this is towards the kitchen. So if you want to go into the kitchen, you swing it to that direction, and here in the front is basically the restaurant, or where the customers will sit in, so they can swing it in any direction. It can swing that way towards the kitchen, or it can swing forward towards the common area. Okay. All right, so if someone is pushing this door, the air for instance, then the liquid mercury that's trapped inside the capillary tube is not going to go out. Okay, so this air therefore is present, and it's pushing the liquid in so that this mercury right here will not drain out fully. Okay, how much force is it pushing? It's going to be pushing the mercury at this magnitude, 760 millimeters of mercury. Now, for those who are not aware of what mercury feels like, mercury is really dense. It's denser than water. And so you could imagine that with this much mercury inside, the air is really pushing that much force. Okay, because you have a heavy person pushing to the other direction. Okay, so mercury is pushing this way, air is pushing the other way. Okay, 760 millimeters of mercury. And because of that, we honor Torricelli and say that 1 atmosphere is pretty much equivalent to 760 millimeters worth of mercury. Okay, or in order for its name, we call it Taurus. Okay, Torricelli, okay, the discoverer. Okay, so we can actually convert from one unit of measurement to another using this as our conversion factor. So let's try to do some exercises before we move on. Okay, so say for instance the pressure of gas inside a tank if we stick a pressure gauge here, it says 1415 millimeters of mercury. How much do you think it is in kilopascals? All right, so let's take a look at the definition of kilopascal. We said that 1 atmosphere is equivalent to 101.3 kilopascal. We also said that 1 atmosphere is equivalent to 760 millimeters of mercury. Therefore, these two must be equal to 1 atm, right? So these two must be equal to each other. So let's try to use that as our conversion factor. How much kilopascal are present in 1415 millimeters mercury? So since millimeters mercury is the given information, then millimeters mercury will be our denominator, and the top one will be our kilopascal. Okay, so we have here 760 is a exact number. This right here is a truncated number. It has 4 significant figures. Our data has 4 significant figures, so our answer must be rounded off to 4 significant figures as well. This cancels out, and what we're left is the unit kilopascal. Okay, so I have 188.6 kilopascal. All right, so we have move on to the second problem. We have a high-performance road bicycle tire. It's inflated to a total pressure of 125 psi. Convert this to its equivalent millimeters mercury. 125 psi. We said that for every 14.69 psi, that's equivalent to 1 atm, and 1 atm is also 760 millimeters mercury. 14.69 psi is equivalent to 760 millimeters mercury. Remember, this 760 is our exact definition of 1 atmosphere, and so we don't count that as its significant figures. The given data has 3 sig figs, the psi has 4 sig figs, and so your final answer will have 3 sig figs as well. So 6466.98 millimeters mercury. Round it off so that it will have 3 significant figures. So round it off to the nearest tenths. That will be 6.47 times 10 to the power of 3 millimeters mercury. That's your final answer.